Okay guys, so let's start. I've turned on the recordings. Okay, so let's do a quick revision of what we covered yesterday. So let me start with the binomial theorem. So we saw the binomial theorem yesterday. What is the binomial theorem? So binomial theorem is a way to calculate probability. So let me talk a little bit more about binomial theorem, little bit more from what I covered yesterday. So binomial theorem is known as binomial theorem because it is used for 0-1 trials. Okay, or also known as success failure trial. Since there are only two values to be taken, it is also known as binomial theorem. Binomial means two. Okay, so it is a theorem which helps us calculate probabilities in case of 0-1 trial or success failure trial. Now why am I calling it a 0-1 trial? This is because all the examples we saw yesterday were all either success or failure trials. So for example, when you toss a coin, okay, when you toss a coin and when you talk about getting heads, when you talk about getting heads in tossing a coin, the heads that you are referring to is a success because that is what you are referring to, that is what you are counting, and tails is a failure. Okay, getting a tails is a failure. So this is a success failure trial, or you can say 1-0 trial. Heads is 1, tails is 0. Similarly, when you talk about getting a 6 in a dice, okay, when you talk about getting a 6 on a dice, getting a 6 on a dice is a success for you and everything else is a failure. Okay, getting from 1 to 5 is a failure. So here also you are talking about success and failure, or 1 and 0. So hence this also comes under binomial theorem. Okay, so that is what binomial theorem is. It helps us calculate probabilities in case of binomial outcomes or 0-1 outcomes or success failure outcomes. Okay, so yesterday we don't have to go to the derivation of the formula, but yesterday we saw the formula to get the probabilities in binomial theorem. It was NCR p to the power r 1 minus p to the power n minus r. So this formula is not very difficult to remember. Okay, so NCR and then probability to the power r, this r goes here, and then 1 minus p to the power this n minus r. That is what I have written here. So not very difficult to remember. If you try, you can. Okay, so where n is the total number of trials, n is the total number of trials, you have r, which is the number of successes that you are looking for. R is the number of successes. Okay, and p is the probability of success in one trial. P is the probability of success in one trial. Now compare this with the example that we talked about yesterday. We talked about the example of getting 17 heads in 20 tosses. Okay, so since we are talking about heads here, getting a head is a 1 for us or a success, and getting a tails is a 0 or a failure for us. Okay, so hence we will follow the binomial theorem to get this probability. Now we will use this formula NCR. So n for us is 20 because total we are tossing 20 times. So 20C, and we are talking about getting 17 heads. So I'll write 17 here. Then P is the probability of success in one trial, which means probability of heads in one trial. So what is the probability of head in one trial? It is 50%. Okay, it is 50%. So this will be 1 by 2 to the power 17. This r comes here, and then you have 1 minus 1 by 2, which is also 1 by 2. You will have 3. So this is the probability of getting 17 heads when you toss a coin 20 times. Okay, so this we get from the binomial theorem. Okay, so why did we learn the binomial theorem? We learned binomial theorem because we wanted to understand hypothesis testing. So what is hypothesis testing? Hypothesis testing is a concept which allows us to make a conclusion about something. Okay, which allows us to make a conclusion about something by taking probabilities into consideration. So how does it work? So we initially start with some assumptions. We assume something and we then start out. So the first assumption that we make is called the null hypothesis. Okay, so this is always the status quo, or the most general situation. Okay, so that is what we assume to be the null hypothesis, and then we have an alternative hypothesis which is opposite of that. Okay, opposite of null. That is the alternative hypothesis. After this, we find p-value. The definition of p-value is assuming null to be true. So we assume null to be true. The probability of the alternative or more in its direction. Okay, this is the p-value. This probability that you get is the p-value. So remember this, or more in the direction of alternative. So you will have to remember what is the direction of alternative. So given the question, your question will always have a normal distribution, and from the normal distribution, for example, in this particular question that we have, getting 17 heads in 20 tosses of a coin, here our null hypothesis will be, we will start with the assumption that coin is fair. This is our null hypothesis because we mostly see a fair coin. So what would happen when a coin is fair? The probability of success will be 0.5. 0.5 will be the probability of success if coin is fair, or you can say probability of head is equal to 0.5. Okay, opposite will of course be coin is unfair. Opposite will be coin is unfair, or probability of heads is greater than 0.5. This is what I write. Why did I write greater than 0.5? Because looking at the question, I obviously, it is safe to assume that since you are getting more heads than tails, the coin is biased towards heads. That is why I have written this. If I was not sure of that, I would have written probability of head is not equal to 0.5. But since I'm sure that heads has a higher probability, and so I'm observing 17 heads out of 20 trials, hence I have written this. So hence, now you would find the p-value. So you will assume that the coin is fair. So the moment you assume that the coin is fair, you get probability of head as 0.5. So you have assumed this. Then you find the probability of alternative. So what is the alternative? The alternative is that you get 17 heads out of 20 trials, but also more in its direction. So the direction of alternative means, so this is the alternative. Look at this statement I have written here. This is the alternative. This means that you will get more and more heads because probability of head is greater than 0.5. So you will get 17 heads, you will get 18 heads, you will get 19 heads, and finally you will get 20 heads. You cannot get more than 20 heads because you are tossing it 20 times. So all of this will comprise of the p-value. You will add the probabilities of each one of them, and the sum is what is the p-value. So now you can use binomial theorem for each one of them. So for this you will have one binomial theorem for this one, for this one, and for this one. And then finally you will get 4 probabilities as output. All those 4 if you add, that is what is called p-value. Okay, now what do you do after calculating p-value? So after calculating p-value, what does it mean? What does the p-value mean? The p-value means that assuming null to be true, what is the probability of seeing a result like the alternative or more in its direction? Now if that probability is very small, we reject the null hypothesis. Okay, so you can remember that by this small little poem. So p low, null go, which means reject. Okay, p high, null fly, which means you accept. So using these two lines, if you remember, and if you get a very small p-value, you reject the null hypothesis. So usually 5% is taken as the threshold. If you get a p-value less than 5%, you reject the null hypothesis. And if you don't get below 5%, you fail to reject the null hypothesis. Now, you might be wondering, why am I saying fail to reject the null hypothesis? Why am I not saying you accept the alternative hypothesis? So there is a specific reason to this. So the reason is in the terminology. Basically, it means the same, but the reason is in the terminology. So for example, in the judicial system, whenever a accused comes to the court, so the judicial systems also follow the hypothesis testing. Whenever an accused comes to the court never assumes that the accused is guilty. The court always assumes that the accused is not guilty, and it is up to the prosecution to prove that he is guilty. By default, the person is innocent. It is up to the court to prove that he is guilty. Only then he will be punished. Otherwise, he will be set free. Okay, so the same concept. So the courts never say that the person is innocent or the person is guilty. The courts will say that given the evidence, the person is not guilty. Okay, so that is why we say we either reject the null hypothesis or we fail to reject the null hypothesis. So the courts say that the person is innocent, or the courts say that given the evidence, the person is found to be guilty. Okay, so it's just the terminology. You don't have to worry about it a lot. So we either reject the null hypothesis or we fail to reject the null hypothesis. So that's the terminology that is used. Then the third concept that we saw yesterday was that of outliers, right? So we saw how outliers influence data. So for example, mean is heavily influenced by outliers. So if you have outliers in your data, and if you're taking the mean of all of them, the mean will be skewed or will get pulled towards the outliers. Because there are a few outliers, the mean will get pulled towards the outliers. And then we saw the right-tailed histogram. The right-tailed histogram, which is basically a histogram which has a few outliers on the right hand side. By outliers, I mean the values which are very different from other values which are very high from other values. Those are outliers. So for example, if you have a few common people and we are talking about income of this group, and let's say one of the person is Bill Gates, then obviously you will have one outlier there who is Bill Gates. Okay, so if you calculate the mean of that group, the mean will turn out to be very high because Bill Gates' income will pull the mean towards a very high number, whereas the other people may not be as rich as him. So that is what is a right-tailed histogram. So in a right-tailed histogram, the median is always less than the mean. So median will not be influenced by outliers. So for example, if you have these numbers, and if you calculate the average, you might get some average, and if you calculate the median will be 5 for these numbers. Now it doesn't matter if this is 9 or 90 or 900 or 9000, the median would still be 5. The median of these numbers will still be 5, doesn't matter what this number is. Okay, because median is the middle number, so it doesn't matter what this is. But mean, of course, will not be the same. The mean will keep changing. So now, for example, since you have 9000 here, if you calculate the mean will come to be a very big number, above 1000. So that is why I say that the mean is influenced by outliers, but the median is not. Okay, what else did we cover yesterday? Okay, we covered uniform and normal distribution, and we covered z-test also. Okay, the next concept we covered was standard deviation and variance. So what is standard deviation? We saw what standard deviation is. It is a parameter which is used to measure the variance in a data. Okay, so whenever you have numerical data, data which is measured in terms of numbers. So for example, somebody's the age of a group of people, the weight, the height of a group of people, the income of a group of people, whatever. So if you want to measure how much variation is there in that group, is the group having the same value of the variable, or is the value varying with respect to individuals? And if it is varying, how much is it varying? Is it varying a little or is it varying a lot? So those those values you can measure using this parameter called standard deviation. Now, what is the formula to measure standard deviation? We saw the formula also. So the English definition is root mean square of deviations from average. So this is the formula for standard deviation. And if you have to write it in maths, you start from the right hand side. So first is you calculate the average, and then deviations from average, you calculate the deviation from average of each individual point that you have, and then you calculate, you take the square of it, then you take the mean of it, and then finally you take the root of it. And of course you will have a summation here because deviation from each point you will be calculating. So this is the formula for standard deviation which we saw. This measures the variability in a group of data points. And then we also saw what is variance. So variance is nothing but a similar parameter as standard deviation. The interpretation, everything is same, it is just in standard deviation whole square. So if you don't give the square root in standard deviation, it becomes variance. Okay, next we saw what is a normal distribution. So we saw what is a normal distribution. A normal distribution is one for which if you draw a histogram, it would look like a bell curve. It would look like this. So why is this so important to us? This is very important because a lot of variables in nature and businesses, they follow such a distribution. So for a lot of variables, if you draw the histogram, it would look something similar to this. So that is why this forms the core of a lot of concepts in statistics. So for example, if you toss a coin 100 times, and if you repeat that operation multiple times, if you toss a coin 100 times, and if you do it, let's say 10 times, so 10 times you toss a coin 100 times, okay, and if you keep measuring how many heads you are getting, you would see that it would follow a normal distribution. Okay, so why is this so important? Because if we know the average of a normal distribution, and if we know the standard deviation of it, if you know the standard deviation of a normal distribution, we can easily calculate the proportion above or below any particular number. So that is why this is so important. So we saw yesterday that if we go one standard deviations on both sides of the average, we get 68% of the data. If we go two SDs away on both sides, we get 95.5% of the data. And if you go three standard deviation, so plus minus, let me write. If you go three standard deviations on both sides, you get 99.7% of the data. Okay, so you get basically almost everything. So that means I can mention that if you go three standard deviations away, you get almost all of your data. Okay, if you go three standard deviations away from the average on both sides of a normal distribution, you get almost all of your data. Okay, because 99.7% is almost all of your data. Okay, so this is what normal distribution tells us. So any variable, if you know that the variable follows a normal distribution, then we can easily use these stats we can use. Now what about if you are asked something which is not which is not either of the three, which is not one SD away or two SD away or three SD away? In that case, you can always use a software. You can use Python or you can use R or you can also use Excel to calculate the proportion. So the formula that we saw yesterday in Python to use this particular thing in Python is, so we used norm dot CDF, cumulative distribution function, and then we used to write the z values. So we'll talk about z values now. We used to give the z values to calculate the probability, right? So we used to calculate the probabilities, or the proportion, you can say, the proportion. Okay. So what are z values? That brings us to the z test that we saw yesterday. So z test, it's a very simple test. It's a very simple test where you just find out what the z value is. So what is a z value? Z value is how far is your particular point, the point in consideration. How far is it from the average in terms of standard deviation? Okay. How far is the point from average in terms of standard deviation? This is what it measures in terms of standard deviation. Okay, how do you find this? You find z value using this formula, xi minus x bar divided by standard deviation. So whatever point you are referring to, whatever point the question refers to, you take that as xi, and this is your average, and of course this is your standard deviation. Then you get z values. You put the z values here and you get the proportion of data below the point. Okay, always remember, cumulative distribution function always gives you the area from the left hand side. Okay, so if you want the area on the right hand side of a particular point, you will have to give 1 minus this particular value. Then it will give you the area on the right hand side. Since we are talking about proportion, this 1 means 100%, and whatever this proportion is, it will mean a percentage. Okay, so this is z value, and this entire thing that we see here is called a z test. Okay, z values are found from a z test, and that is how you use it in a normal distribution. Okay. So anything else did we cover yesterday? Apart from this, is there anything else? Guys, anything else did we cover? Yeah, I think that is all that we covered. Okay, so these are all theory, which will help you understand machine learning better. Okay, so in machine learning we will focus not on just the codes, because the codes are pretty simple, 2 3 lines of code in all algorithms you will see, but we will try to focus and understand the maths behind each of the codes. Okay, that is where all this theory will help you understand the algorithms better. Okay, so let's begin today's topic. So we will talk about a few other statistical concepts today. So first we will talk about box plots. What are box plots? So these are very important plots which help us understand the data better, which mostly help us detect outliers. So they help us detect outliers in data. And then we will also talk about another very important algorithm in statistics, the central limit theorem. Okay, so as the name suggests, this theorem is very important. It is central to all of statistics. Okay, so this algorithm will help you understand the importance of normal distribution in statistics. Okay, so what are box plots? Box plots are plots which help us identify outliers. Okay, they help us identify outliers in the data. So remember, we were talking about outliers yesterday. So if you have outliers in your data and if you draw the histogram for it, you get a right tail or a left tail depending on whether the outlier is very large compared to other values, or if it is very small compared to other values, you get a left skewed histogram. So this is a left skewed histogram where you have a few values which are very small compared to the other values. So how do you detect these outliers? How do you identify? So for example, let's say if you have 1, 5, 10, 11, and let's say you have 500. So obviously it looks like 500 is an outlier because this is very large compared to the other values. But how large should it be? Is 200 also an outlier here? Is 50 also an outlier here? Because 50 is also very large compared to the other values. So where is that threshold which helps us decide what is an outlier and what is not? That is decided based on box plot. Okay, so how do we draw a box plot? Let me show you. So this is always drawn for a numerical variable. Always remember this. This is also drawn for a numerical variable, a variable which is measured in terms of numbers. So box plot for values which are not numerical, for example, gender, male and female. So box plot for such values will not make sense. So we only talk about box plot for variables which are numerical in nature, which take a number. Okay, so this is how you draw a box plot. It is also known as box and whisker plot. Okay, so these lines that I have, so this is the box, and these lines that I have drawn here are also known as whiskers. So it is also known as box and whisker plot. Okay, so what do you have on the y-axis? On the y-axis, you have the variable, whatever variable you are referring to, you have that variable on the y-axis, and there is no x-axis here, it is just one axis. Okay. So how do we draw this? How do we draw the box plot? So we have this plot where we have a box here. So this box has 50% of your data. Okay, 50% of your data will come within the box and 50% will be outside of it. Okay, so 50% is within the box and 50% is outside of it. So Amit is asking why is 50% inside the box and why is 50% outside of it. So Amit, there is no reason for it. This is what is the standards basically. Okay, they have set this as the standard because so that everybody follows the same proportion, that 50% will be inside the box and 50% will be outside of it. There is no particular reason why it is 50% inside. Okay, now this particular value, the value at the lower end of the box, this is 25th percentile. This is 25th percentile, which is also known as Q1. Q1 means first quantile. Okay, Q1 means first quantile. Then you have the upper end of the box. This is Q3 or 75th percentile. 75th percentile. Q3 is known as third quantile. Okay, and in the middle of the box you will have a dark line. You will have a dark line in the middle of the box, that is called Q2 or the 50th percentile or median. Okay, so Q2 is the 50th percentile or second quantile. Okay, this is what these, so this is Q3, this is Q2, and this is Q1. Now what are these lines? Now this distance, the distance between Q3 and Q1, this is known as interquantile range. Okay, so IQR stands for interquantile range. This is IQR, it is interquantile range. This is the distance between Q3 and Q1. Okay, now you might be wondering what is this particular distance. So the distance from here to here, this is 1.5 times IQR. Okay, this distance from here to here. Similarly, this distance from here to here is also 1.5 times IQR, the interquantile range. That is this distance. Okay, now you might be wondering what is outliers in this case. There is no difference, Arpita, they are same. So quantile is also referred to as quartile. Okay, they are both the same things. Quantile or quartile, it means the same. Okay, so now you know all the measurements here. What are outliers now? Any point which is below this, any point which is below this, or any point which is above this, these are outliers in the data. Okay, so I can say what are outliers? Outliers are any point which is less than Q1 minus 1.5 times IQR, or any point which is greater than Q3 plus 1.5 times IQR. This is an outlier. Okay, so any point which is below this, how would I write? I can write Q1, this point is Q1, I know this point is Q1, so I can write Q1 minus this distance, which is 1.5 times IQR. This is an outlier. Similarly, we can have outliers on the higher end also, so I can write Q3, this line, plus 1.5 times IQR, this distance. Any point which is above that, which is greater than that, is an outlier. So this is why box plot is used. Okay, this is how you use box plot. It is very easy to draw box plots. So you write plt.boxplot and you give the value of the variable. Any list you can give here, or you can give a column of your data frame. So let's say data frame, and you can give age. So imagine you are doing a box plot for age. You can write this. What is plt? This comes from the matplotlib library, which we have covered already. So import matplotlib.pyplot as plt. So that plt is coming here. So from matplotlib plt.boxplot, and you write this. You write this column or a list. This can be a column or it can be a column from a data frame, anything. And you will get the boxplot with these. It would look like this. Okay. So any doubts, guys, on boxplots? Any doubts do you have? So just take a moment, look through this, and tell me if you have any doubts. Okay, now let's move to the next concept for today, which is again very important, which is the central limit theorem. Now the central limit theorem is the most important theorem in all of statistics. Okay, this is the most important theorem. So I will first discuss the theory of the theorem, and then I will prove it in Python. So in Python I will also prove this theorem using some codes. Okay, it is very easy. It's not a difficult theorem, and you will find the application of this theorem once we start with machine learning. So right now it will only be theory, and the application of it we will see next week. Once we start with linear regression and logistic regression, we will see the application of central limit theorem. Not just central limit theorem, we will see the application of hypothesis test also, that we studied yesterday. Hypothesis test, z test, the application of all of these we will see once we start with machine learning, which will be from next week. So the central limit theorem, let's say. So let's say we have a population. Okay, we have a population. So what is a population? A population refers to a huge data point, a data point which is huge. There are too many values. So for example, let's say if you want to find out the income of a software professional in Bangalore, so your population will be all software professionals of working in Bangalore. That would be your population. So population refers to a huge data source. Okay, so all software professionals may be your population. Let's say you want to study them. Okay, and then we have another terminology called sample, which is sample, which you would already know from the name. Sample means a small portion of the population, a small portion of the population. So why do we use a sample? We use a sample because whenever you want to study a population, it is not feasible to study every individual in a population. So for example, let's say you want to find out what is the average income of a software professional in Bangalore. You cannot go and ask everybody in Bangalore, every software professional in Bangalore, what is his income. So what you would do, you will select a sample and you will ask only that sample. So why would you do that? Just to be more practical, because it is not feasible to ask everybody. It will require huge costs. So you will ask a sample. Now, how do you decide which points to include in a sample? Now that has to be very cautiously decided, because a sample should represent your population. Now you cannot go and ask only let's say the vice presidents of companies. So they are also software professionals. You cannot go and ask just those people what is their income. That would not be a true representation of all software professionals in Bangalore. So what you would do, you would keep a mixed bag. You will ask some freshers, some mid-level professionals, some high-level professionals, so that it actually represents the actual population. Okay, so that is how you select your sample. There are different techniques which are used to do this. We'll not go into the details. That is pure statistics. We'll only see what is important from a data science perspective. Okay, so let us see what is central limit theorem. The central limit theorem tells us that no matter what distribution of population, so let me write it down. No matter what is the distribution of population, if we take many samples of size at least 30, the sample mean and sample sum will follow a normal distribution. Okay, so this is what the central limit theorem tells us. This tells us that no matter how your population distribution is, let's say you want to see how is what is the income of a software professional in Bangalore. Now that distribution, the income of all software professionals in Bangalore may not have a normal distribution. It most usually will not have a normal distribution. So the distribution of all software professionals in Bangalore may probably look like this. You will have a lot of maybe like this. You'll have a lot of people who have, let's say, incomes below 5 lakhs. So all the freshers, we obviously have more freshers in the industry, more entry level professionals in industry than managers. And then you will have a few outliers, a few, maybe these are the CEOs of companies and all. So they will have very high income. It would look probably something like this, a right skewed histogram. So this is the population's histogram, the distribution of population. Now the central limit theorem tells us that no matter what is the distribution of population, so whether it is normal or not normal, right skewed, whatever, if we take many samples of size at least 30, so what are we trying to do? We are trying to take many samples from this population. So let me take sample 1. I have taken sample 1. I have taken sample 2, and all the way I have taken, let's say, 100 samples. I have taken 100 samples from this population. Now what does this theorem tells us? If we take many samples at least of size at least 30, that means in each of these samples, so imagine this is all software professionals in Bangalore. So what you will do, you will take many samples. Okay, this is one sample, this is second sample. You will take many samples, S1, S2, S3, S4, and let's say S5. So if you take many samples of size at least 30, so that means in each of these samples you will have to include at least 30 individuals. Okay, not less than that. In each of these samples you will have to include at least 30 individuals, is what the theorem tells you. Then the sample mean, if you take the mean of all the samples now, so you have taken sample 1 till sample 100, and let's say you are taking the income of this sample, the income of this sample, the income of this sample, and so on. Okay, so the average income. So S1, let's say it has 50 individuals. Okay, so let's say this has 50 individuals, this also has 50 individuals, this also has 50 individuals. So in sample 1 you will get 50 different salaries. You take the average of all that salary, sample mean. You take the average of all those 50 individuals. Similarly, in sample 2 also you have 50 individuals. Take the average salary of all those 15 individuals. And then whatever number you get, you plot a histogram using those numbers. So using these numbers, you plot another histogram. Okay. So what does this tell you? This tells you that the sample mean will follow a normal distribution. So this distribution of the mean of the income will follow a normal distribution, even though the population did not follow. So you see the population was right skewed, but when I draw the histogram of sample mean or the sample sum, similarly I can do for sample sum also, this will definitely follow a normal distribution. This is what central limit theorem tells me. Okay. No, I mean, there is no minimum number of samples. Okay, the more samples you take, the more easily you will be able to draw a histogram. Okay, if you take just 2 samples, you will not be able to draw a histogram based on 2 samples. You will have just 2 numbers, let's say 5 and let's say 10. So how will you draw a histogram? To draw a histogram, you will have to take more and more samples. Only then you will get the bar, right? You will get some height to the bar. So that is why if you take many samples, many means many, so the more the better. Okay, maybe hundreds of samples. Okay, because if you take very small number of samples, you will not be able to draw a histogram properly. At least 30. Okay, so Arpita, it says at least 30. You can take any number above 30. So I have taken 50 here. At least 30. Okay. So this is why the normal distribution is so famous in statistics, because eventually, even if your population is not following a normal distribution, you can always reduce that variable to a normal distribution by using the central limit theorem. Yes, Arpita, all the samples should be of equal size. Correct. So now let me try to prove this algorithm to you guys. So I will use Python to prove the algorithm. How will I prove the algorithm? Because I don't have a population, I can always generate a population. I can generate a population using random data. So using random numbers, I will generate a population, and then using that population, I will prove the central limit theorem for you guys. Just give me a moment, guys. Okay, so this is where it starts. So first, what I have done, let's prove CLT using an example. So this one, whatever I have written here, we have already seen this yesterday. This is just binomial theorem. So what I will do is I will create a population using random numbers. Okay, I will create a population using random numbers, and then from that population I will start taking many samples. Okay, and then I will plot the average of the samples. I'll plot the histogram of the average of the samples, and then we will see that that histogram of the samples will turn out to be normally distributed. Okay, so what I have done here is, so I have used the rand int function. this generates a random number between two integers using a uniform distribution. Okay, so I'm generating a population from a uniform distribution. Remember uniform distribution, this is how it looks like. It stays flat. This is what we saw yesterday. So I'm generating, see how many random numbers I'm generating, almost 10 lakhs. I have generated 10 lakh random numbers from a uniform distribution. Okay, so this is a uniform distribution. You see, this is our population. So our population has 10 lakhs random numbers. Okay, I've used the randint function from the random library. Okay, so this has 10 lakhs random numbers taken from a uniform distribution. So this is your population. Your population is a uniform distribution. Now let us start taking the samples. Now let's select some random samples from the above population. We will select a sample of size greater than 30. So let's select a sample of 50 numbers from X above. So what I will do, I will select 50 random elements from the list X, and I will repeat that process multiple times. Okay. So remember, what did we see? If you take many samples, many means hundreds of samples, the more you take, the better. Okay, this is required only to plot a histogram, because if you take just one sample, how will you plot histogram for one sample? You will just get one number, which is the average of that sample. You will not be able to plot a histogram using just one number. How will you find out whether it is normally distributed or not? So you will have to take many samples. Okay, so here what I have done, I'm taking 5,000 samples. 5,000 samples from the population, from these numbers I am taking. So x has those numbers, this x has those numbers. So from x I am taking 5,000 different samples, and each sample is of size 50. Okay, so there are two things here. Notice, one is large number of samples, so this value is 5,000 for me. This value is 5,000 for me, and this value is again 50 for me. Okay, so I'm taking 5,000 into 50 total picks. So for I in range 5,000, this is just a normal for loop I've used. So for I in range 5,000, I'm using random dot sample function. What does the random dot sample function do? The random dot sample function, it just takes as many numbers as you specify from a list. So my list is X, which is the population. So this is my X, which is the population. From X, it will take 50 numbers. Okay, and this process will be repeated 5,000 times, because I have put this inside a loop, and that loop runs from 0 to 4,999, or 5,000 times. And then I'm taking the average of all those numbers. So all these 50 numbers I'm putting in Y, and those average of that Y I'm putting it in another variable called AVG. Okay, and at last I'm drawing a histogram of that AVG. Now you see, look at the histogram. It looks like a normal distribution, even though your population was not normal. But when you took large number of samples of size at least 50 or at least 30, you saw that this average of the samples, it started looking like a normal distribution. So this is the central limit theorem. Okay, this is the central limit theorem, which tells you that if you take large number of samples from a population, whatever be the distribution of population, doesn't matter, the average of the samples or the sum of the samples. So here I have shown for the average. Even if you had taken sum of the samples, both would look like a normal distribution irrespective of the population. Okay, so any doubts here, guys, on the central limit theorem? We will see the application of this next week. So I'll pause here for a moment, just read this multiple times, see if you have any doubts, tell me. Yes, Arpita, that is true. That's what I have written. No matter what distribution of population. So it need not be uniformly distributed. It can be anything. Okay, it can be anything. That's why I have written clearly that no matter what distribution of population. Read this line. So whatever is the distribution, here I have shown with respect to uniform distribution, but it can be anything. Okay, so this can be anything. It can be anything like this also. Even if the population was like this, still it would have given you a normal distribution. Still it would have given you a normal distribution. So this doesn't matter. This can be anything. Okay. So we will see the application of this next week, and then you will realize the importance of the central limit theorem. It is very important to understand machine learning algorithms because it tells you how important is normal distribution for you. Okay. So I will share these codes. Just go through these codes. Make sure you understand each and every line, and you can keep changing this. So for example, here I have shown you this with respect to a uniform distribution. This is with respect to a uniform distribution. You can keep any other distribution here. So instead of using rand.int, so this basically gives you integers from a uniform distribution. Instead of this, if you give any other distribution or if you create your own data here, even then this would look the same. Okay, so you can try out with different combinations here and you will find that it still gives you a normal distribution at the end. Okay, now let us see one a very easy concept on the variables that are used in statistics. Okay, the variable types in statistics. This is easy, this is not difficult. Okay, in statistics you can say, or in data science also. This is in statistics or data science. Now They are broadly divided into two types. One is quantitative, okay, and one is qualitative. So what is quantitative? As the name suggests, quantitative means these are represented by numbers, okay. These are numbers. Qualitative means these are not numbers, okay. Quantitative can be anything like age, weight, height, income, salary, whatever, okay. These are all quantitative variables because they are measured in terms of numbers. The ratings that you give to an app, these are all quantitative. They are quantities. Qualitative is everything else. For example, gender, male, female, color, yellow, blue, green, small, medium, large. So those are all qualitative variables. Okay. Now within quantitative, you have two categories. You have two categories within quantitative. One is continuous and one is discrete. Okay. So what is continuous quantitative variables? Continuous quantitative variables are variables which can take any decimal number. Okay, so for example, height. When you talk about height, can height take any decimal number? Yes, of course. So you can have somebody who is 5.5 feet tall. You can also have somebody who is 5.6 feet tall, and so on. So this is all making sense. These are all decimal numbers and it is making sense. So these are continuous variables, okay. Similarly weight, similarly age, and so on. Now some quantitative variables cannot take decimal numbers. So for example, number of cars you have or somebody has, number of cars, you cannot have 1.5 car, it doesn't make sense. Or number of children, number of family members, number of dependents a person has, okay. There is no decimal place that can exist in such variables. These are known as discrete variables. So for example, when you download a app from a play store, you cannot give decimal ratings. You can either give 1, 2, 3, 4 or 5 rating. You cannot give 4.5 rating. So one individual cannot give 4.5 rating. Overall, it can show you 4.5 based on the average of everybody, but one individual can only give a discrete rating. Okay, so these variables are known as discrete variables. Do you follow, guys? Do you follow quantitative variables, continuous and discrete? Any doubts in these two? Okay, so continuous variables are any variables. So first quantitative and qualitative, that is pretty simple. Any variable which can be represented as numbers or which are measurements, which are quantities, they are quantitative. Anything else which are not quantities, for example, male and female, you cannot say male is 1 and female is 0, or the otherwise. So that is qualitative because that is not number. Anything which is a number is quantitative. Now what is continuous within quantitative? Continuous within quantitative means it can take any decimal value also. So your height, your weight, it can take decimal values. So it is a continuous variable, okay? It is continuous in nature. But discrete means it cannot take decimal values. So for example, number of children, number of dependents a person has. Nobody can have 1.5 children or 2.5 children. They can either have one children, two children, or three children. Okay, so those will come under discrete. So for example, the ratings that you give to an app, those are also discrete because you can only give 1, 2, 3, 4 or 5 rating. You cannot give rating in decimal numbers. Okay, is that clear now, Vikram? I gave the same examples because this is, yes, correct. Okay, that is correct. So discrete can take only integer values is what you can say. Discrete can take only natural numbers. It is the count of something. So discrete means it is count. So count means it can only take natural values, right? It cannot take negative decimal places. 1.5. It doesn't make sense. 1.5 of something doesn't make sense. Okay. Now on the other side, let's talk about qualitative. On the qualitative side also there are two types. One is nominal, one is ordinal. Okay. So what are nominal variables? So nominal variables are all qualitative variables which do not have any order. So for example, male, female, or gender, for example, gender. In gender, there is no order. So for example, you cannot say that female is greater than male or male is greater than female. There is no order. We are not talking about alphabetical order here. Okay, don't consider alphabetical order. We are talking in terms of business. In terms of business, you cannot say that male is greater than female or female is greater than male. So it is nominal because there is no order. So for example, colors. You cannot order colors. You cannot say red is greater than blue or blue is greater than red. Okay, so it falls under nominal variables. Ordinal, as the name suggests, it comes from the word order. Okay, here there is a order in the variable. So for example, if I say low, medium, large, so we know that low is lesser than medium and medium is lesser than large. So there is a order associated with the categories. There is an order associated in the variables, and hence it falls under ordinal variables. Okay, hence this will fall under ordinal variables. But male and female, there is no order. Colors, red, blue, green, there is no order. So these are nominal variables, and wherever you will see some order, you can say it is a ordinal variable. Is it making sense, guys? Yes, correct, Harsh. Nominal means no order. Now let me ask you a question. A question on this. Let's say we are talking about gender. Okay, and I write male as 1 and female as 0. I've just represented male as 1 in my data and female as 0 in my data. Okay, and now your data only has ones and zeros, meaning male or female. Now what kind of a variable is this? Can you tell me what kind of a variable is this? Okay, so the answer to this is that it is still a nominal variable. Okay, just because I have represented it as 1 and 0 doesn't mean it will be discrete. Okay, this is wrong. It is still a nominal variable. Why? See, the moment, so guys, understand this in terms of business. The moment you say male is 1 and female is 0, and you say that they are discrete, this means that male is greater than female, right? Because 1 is greater than 0. But this is not the case, right? This is not the case that male is greater than female. This doesn't make any sense. So it will always be nominal. Even though you have represented it as 1 and 0, this is just a representation. The numbers do not really make any sense. This is just you are changing the value from m to 1. Okay? The numbers don't have any numerical sense here. So this is still nominal. Okay? There is no other numerical sense to the numbers that is given. So it is still a nominal variable. So just changing it or representing it in some other way doesn't mean that the data type will change. The data type, the variable type still remains the same. It is still nominal. Okay? So remember this. Okay, so Harsh wants to see one more example between discrete and nominal. Okay, so they are totally different. For example, what example should I think of? So give me a moment. So you want an example of discrete and nominal. So nominal is again, what should I say? What can be nominal? So gender is nominal, color is nominal. Let's say employee ID, for example. Employee ID, yeah, this is a good example. So what would employee ID be? So let's say employee ID of people is like this. This is the employee ID that you have in a company. What kind of a variable is this? What do you think? 1001, 1002, 1003. Let's say this is how the employee ID goes. What do you think is the data type of this? Yeah, bank account number, and so on. Okay, Vikram says it is continuous. Employee ID, do they take decimal places? I don't think so. I have never seen employee IDs taking decimal places. Okay. So what kind of a variable are they? Employee ID, bank account numbers, what kind of variables are they? Okay, Sinod says it's nominal. What about the others? That is correct, Vikram. Continuous should accept decimals also. Harsh says that account number or employee ID is not nominal. Why? Then what are they, Harsh? Which one do you think they are? So the answer is that they are nominal. Okay, Harsh. So employee ID or bank account numbers, they are nominal. Why? Because these numbers do not have any numerical sense. So when you say somebody has employee ID 1001 and when you say somebody else has employee ID 1005, this doesn't mean that this employee is greater than this employee, right? This doesn't mean that this employee is 5 times greater than this employee. No, we never use that, Sinos. Do you think you use account number to take average? You never take account number to take average, right? Do you take the average of employee number? Will that make sense? Do you take average of employee number, that okay, I have an employee with employee number 1001 and I have an employee with employee number 1005, so their average is 1002.5? Does this make sense? It doesn't make sense at all, right? So any numerical operations on these values will not make sense. So these are nominal. Okay, any numerical, so for example male and female, if you take the average you get 0.5, you get zero point 0.5. Now this doesn't make any sense. What is 0.5? Okay, so that is why we call them nominal variables, because you are just representing them as numbers. The numbers don't really have any numerical meaning. They are just representation. Okay, now is it clear, guys? So don't worry, we'll talk about this a lot going forward. This is not the only time when we are talking about this. So we will constantly be talking about this in every class from now onwards. So machine learning is all about identifying the variable type and then selecting the algorithm. So we'll talk about this a lot in the future also. Okay. So what do you think rating says? Ratings that you give to an app or ratings that you give to a Uber cab. What do you think is that? Is that ordinal or is that discrete? Okay. So the answer to this question is that it can be both. You can take it as both. Okay, so there is a confusion between these two. So if you just go to the internet, you will see a lot of people debate about this. Some people say that it should be ordinal, some people say that it should be discrete. So you can use either, basically it doesn't matter a lot. You can use either ordinal or discrete, both will work. Okay, so there is no answer to this. This is a debate where people take sides. Some people argue that it is ordinal, some people argue that it is discrete. So you can take any and move forward, basically. Okay, because of course this has a order. So rating 5 is greater than rating 1, so this has a order, so it means it is ordinal. But at the same time they are discrete also. They are discrete also, so that is why people take sides and argue. Okay, okay. So now let us talk about what machine learning is. Okay, so I'll briefly describe what machine learning is. So first of all, machine learning is all about finding out a variable, okay, from some other existing variables. Okay, so for example, if you remember from your school days, we always used to solve these kind of equations, right? Y is equal to f of x, and then we used to do something with these. Remember, y is equal to f of x. So this y we used to call it the dependent variable, and this x we used to call the independent variable, because the value of y is dependent on x. If you change your x, your y will change. So we called x as the independent variable and we called y as the dependent variable. So in businesses also this is usually the case. In businesses also this is usually the case, but now we will not have just one independent variable, we will have many independent variables. So we will have something of this sort, x1, x2, and so on till xn, let's say. Okay, so this is what we will be solving, and this is mostly what machine learning is all about. Machine learning is all about finding a dependent variable using some independent variables. Okay, finding a dependent variable using some independent variables. Now how do we do this, or what are the examples of this? First let us see some examples of this. So for example, let's say a bank. A bank will want to know whether a customer who is applying for a loan will return the loans or not. Okay, if a bank is able to find that in advance before issuing loan to a customer, that would be of great help to the bank, right? Because the bank will know in advance whether the customer is likely to pay loans or not. So here, what is the dependent variable? Here the dependent variable is 1 or 0. 1 means he will pay back his loans, 0 means he will not pay back. Okay, he will not pay back his loans. And what is the variable type of this variable? 1 and 0. Tell me guys, what do you think is the variable type of this? Whether somebody will pay his loans or will not pay his loans. What is the variable type of this, from what we learned just before the break? Yes, it is nominal. Okay, it is nominal type, yes or no. Okay, so all yes and no will also come under nominal, because there is no order here. There is no order here, and these quantities do not have any numerical meaning. So this is also nominal. So this is our dependent variable, where the bank would want to know whether a customer will pay loans or not. And what can be the independent variables in this case, guys? What do you think can be the independent variables for a bank to decide whether a customer will pay back his loans or not? So this can be the person's income, right? Obviously, a person returns a loan or not will depend on his income. This will be on his age, maybe. This will be on his previous transaction details. Yes, Hers, that is also right. On his previous transactions, on his bank balance. Yeah, civil scores, correct. Civil scores. Maybe on his profession. Yes, it can be on his profession also. It can be on his number of dependents he has, right? Number of dependents he has. It can be on his gender also, maybe. So it can be dependent on any of these factors or all of these factors simultaneously. So here we have our dependent variable as yes and no, and the independent variable is all of this. Okay, so in machine learning, what we try to do, we try to find this variable, we try to find this dependent variable using these independent variables. Okay, using these independent variables. How do we do that? So the bank, let's say the bank has been running for some time. So what we will do, we will take data from 2010 till 2018. Okay, we will take this 8 years data, and in this 8 years, so this is old data, right? So in the old data we would know whether a customer has paid his loans, his or her loans or not. Whether a customer has paid loans or not in the past, we will obviously know that, because those loans would be complete. So this data we already have one, and we already have whether it is 1 or 0, and we have all of this. So we have our y, we have our all the x's. So we have this in the past data. I'm talking about the past data right now. Okay, what we don't have is this function f, right? We don't have this function f. What is that function which relates the two? So this is what we do. So we know this, we know all of this, so we can easily find this function f. Okay, so this is what is the goal of machine learning, finding this function f which maps your dependent variable with the independent variables. And once you have this f, let's say you have found this f, now what you can do for the new data, let's say 2019 onwards, 2019 onwards, what will you do? Since you know f right now, you can just put this f and you can plug new values of independent variable. So when in 2019 new customers apply for loan, you can get their independent. So you can ask the customer's income. Obviously a bank will ask customer's income if he whenever a customer approaches for a loan, the customer's age, his previous transactions, his bank balance, his CIBIL scores, all of this the bank will calculate, or the bank will ask, and then the bank will simply put these values here in the function, and the bank will get y. So this is what the banks want. So the bank will know in advance whether the customer will pay back his loans or not. Obviously, it will not be 100% correct. Sometimes the model will make error. So this F is called the model. It is called the model. Model means a mathematical function which helps you predict for the future. So using past data, we try to find the model, and once we have the model, we put the new data in the model, and we find the value of the dependent variable. So this is what machine learning is about. Do you understand, guys? So we will see this in details. We will try to find the function f and everything. We will see this in far details, but this is the high level of it. This is what machine learning is all about. This is what we do in machine learning. We try to find a function f which gives a relationship between your independent variables and your dependent variable. And once you have that relationship, you can always put the independent variables and find the dependent variable for future. So you can make predictions for the future. Okay, is that clear, guys? Any doubts, guys? Is that clear? So just give me a moment, guys. I'll be back. So just one moment. Okay, so Sinu has a question here. Just to be clear, these x1, x2, xn are independent variables, and when applying the function or the mathematical model on these variables, you get the value for dependent variable. Yes, Sinu, yes, that is correct. But first, you will have to find the function f, right? First, you will have to find the function f. What is that function f? So you find the function f from past data, okay? Because in the past, you know both dependent and independent. For past data, you both know whether, so let's say customers who took loan 10 years ago, whether they paid back their loans or not, you already know it. And you also know the customer's income, the age, and every details. So you know your y, you know your x. You just have to find function f. What is that relation between the two? Okay. Now once you have the function f, then in the future data you can do that, because in the future you will not know y, you will only know x. In the future you will not know whether this customer will pay the loans or not, because you haven't given him the loans yet. You just know his income, his dependent, his age, his gender, etc. Making sense? No, we are not trying to find that, Chinu. But we will consider that. Don't go into the details of it yet. We will talk about that once we start with machine learning. So this is just the introduction. Once we go into the details, we will start analyzing those things also. But right now, don't confuse yourself by thinking about that. Right now, our goal is to find the function f, which gives a relationship between dependent and independent. Just these two. Okay, that is the only goal. Okay. So now let us look at the different types of machine learning that we have. So let me write ML here. So we have two types of machine learning broadly. One is called supervised learning. Okay. So what is supervised learning? Supervised learning is the case that I referred to. Here you have a dependent variable. Okay. So whatever example I just gave you, that is supervised learning actually. That is not all of machine learning. That is one specific part of machine learning which is called supervised learning. Okay, which always has a dependent variable. So this is where you will see y is equal to f of something. Okay, this is called supervised learning. You have another type which is called unsupervised learning. Unsupervised learning is where you do not have a dependent variable. Okay, so where here we do not try to find anything of this sort. Okay, this is not our goal. Here the goal is just to find patterns in data. Okay, this is the goal. Here the goal is to find patterns in data. The goal is not to find the relationship or the dependent variable, because there is no dependent variable here. This is just finding patterns in the data. Okay, we will talk about this later. So right now we will start with, so next week we will start with supervised machine learning. We'll continue with this for some time and then we will move to unsupervised. Okay, so don't worry about this right now. Right now just focus on supervised learning. So supervised learning is whatever example I gave, y is equal to this. Our goal is to find this function f. This is supervised learning. Okay. Now supervised learning is divided into two parts. One is called regression. One is called classification. Okay. Now what is regression? Regression is when the dependent variable is quantitative, and classification is when the dependent variable is qualitative. Okay, we have already seen what quantitative and qualitative is. So remember, we are only talking about the dependent variable here, not the independent variable. We are not concerned with what the independent variable is, whether it is a qualitative or a quantitative. We are only concerned with what is the variable type of the dependent variable. Okay. So for example, sales of a company. Sales of a company may depend on the number of countries it works in, on the products it has, okay, on the marketing budget of the company and so on, etc. So what do you think is this? Is this a regression problem or is this a classification problem? What do you think sales of a company will be? Will it be a regression supervised learning or will it be classification supervised learning? Sales of a company. Yes, exactly. Because sales of a company is a quantitative variable, right? It will be a quantity. So obviously it will be regression, right? So this will fall under regression. Now within regression, we have several algorithms. We have several algorithms within regression. We have linear regression, we have decision trees, we have random forest, we have KNN and so on, etc. We have neural networks and so on. So we'll learn about all of this one by one. So one week we will focus on one algorithm. Next week we will start with linear regression. Okay. Similarly, you have the bank example which I gave you. The bank example. So which type of a problem is that? The regression problem or a classification problem? The bank example. Whether a customer will repay his loans or not. What kind of a problem is that? Is that a regression problem or is that a classification problem? Yes, exactly. Because the answer is yes or no, right? The dependent variable is yes or no. So obviously that is qualitative. That is not quantitative, that is qualitative in nature. So that is a classification problem. Now within classification also you have several algorithms. Okay. Some of the algorithms are common. They can be used for both regression and classification. So trees, for example, random forest, even KNN. These can be used for both regression and classification. And some are specific. So linear regression is only for regression, logistic regression is only for classification and so on. Okay, so we will talk about these in details from next week onwards. That will be our goal, to analyze and understand each algorithm in details. Okay, so the point to be noted here and to be remembered is that whether a business case study is regression or classification is decided based on the dependent variable. Okay, we are not concerned with the independent variable. The dependent variable decides whether the problem is a regression problem or it is a classification problem. Okay, and all of this comes under supervised learning. Okay, why is it called supervised learning? It is called supervised learning because the independent variables that we have, they supervise the dependent variable. They in some way control the dependent variable, right? So the dependent variables that we have, they in some way control the dependent variable. The independent variables, they control the dependent variable, or in other words, they supervise the dependent variable. Hence it is called supervised learning. Okay, is this clear, guys? No, Sinu, not always. Not always. It has nothing to do with past data or present data. So it is to do with the goal of your study. What are you trying to do? Are you trying to find a relationship between one variable and some other variables? If yes, then it is supervised learning. If you are just trying to find patterns in your data, then that is not supervised, because you are not trying to find any function. There is no dependent variable in that case. You are just trying to find similar groups in the data. That is unsupervised. But if there is a relationship involved, if you are trying to predict something, so for example, the bank is trying to predict whether somebody will return loans or not. You are trying to predict the sales of a company. So you are trying to predict something. That something is the dependent variable. So then it is supervised learning. But when you're trying to find pattern in your data, you're not trying to predict something. You're just trying to find patterns in your data. That is unsupervised learning. Okay. So we will talk about this in detail. So obviously it will become clear. So don't worry about this, because this is what we'll be talking in the remaining of the course. So we have hardly covered 10 to 20% of the course. almost 70 to 80% of the course still remains. So we'll talk about all of this going forward in details, along with a lot of case studies, a lot of homeworks I already have prepared, so which I'll be sharing with you, and you will be practicing on those homework. Okay. So any other doubts, guys? I think this is all I had for today. There was not much. This is all I have. From next week, we will start with one algorithm at a time. So we will start with linear regression from next week. So this is an algorithm which is used for regression problems. We will study this algorithm first, study all the maths used in this algorithm, and then we will see some examples of this. And I'll also send a homework on this. So after this, you will become quite comfortable in linear regression, implementing linear regression using Python, plus all the background theory that you have to know. So this has a lot of maths involved, a lot of calculus will also come. So we will talk about that in the next week. Okay. So let me check, guys. I will try to put a class next week also, since we had missed one class earlier. I will try to put a class on at least one day in the next week. Okay, either Saturday or Sunday. I'll try to put a class on at least one day. Okay, same time. It will be in the same time in the mornings.